Okay, welcome everyone. Today, Tony Bloch from Michigan will tell us about geometry and integrability of Hamiltonian and radial flows.
Thank you, Jim. So thank you for the invitation to IIS and for the opportunity to speak here. So that is indeed the title. So this is work that I did here with Stephen Popp, who's sitting here, and relates to earlier work that I did with Roger Bloch at Harvard, Herman Flasker at the University of Arizona, who is a big integrable systems guy, and Toda, who's now in Shanghai, actually. So this is a work that's sort of at the intersection of several fields. So I'd like to try and sketch out those connections, and feel free to ask any questions as we go along. So as it indicates, it's meant to sort of show connections somehow between geometry and topology and dynamics, and to relate it to the field of total positivity. So it's not directly related to stable polynomials, although some of those dynamical techniques that Stephen and collaborators worked have been used there, and we're thinking about that as well. So total positivity, I'm going to say something a bit about what that is, and Stephen will say more tomorrow and about its connections with other things. So basically, a totally positive matrix is a matrix, all of whose minors are positive, as opposed to the principal minors. That's the essential thing, but it's been developed in lots of different ways, as I'll describe as we go along. And it's related to flows and the topology of Grassmann manifolds and also flag manifolds. So we want to say something about the total positivity when it's applied to Grassmannians and to general flag manifolds, and to say something about how dynamics explains the topology and geometry of these things. So it's also related to convex polytopes and combinatorics, as I'll show you. The twist map is something that also sort of links these things together. So the twist map is something we use to show the Toda lattice flow, which is a Hamiltonian flow, is related to a flow on convex polytopes, but it also plays a role in our work on positivity. And one of the interesting things about the Toda lattice flow, this is a flow, as it suggests, on a lattice, a one-dimensional lattice, but it has a kind of dual Hamiltonian and gradient character. And it's that gradient character that enabled us to say something about the topology of these manifolds. And finally, if I have time, I'll say a little bit more about some other applications, some sort of recent work on Monge-Kantorovich, which is optimal transport, and optimality on orbits in relationship to control theory. So here, just finally, just is a little picture. So this is a permutahedron, which plays a role in the system. And here is something that's not a convex polytope, but it's related to the Toda lattice and says something about the twist map. So if you apply directly, for those of you who know the moment map, to the Toda lattice, you get something that's not exactly a polytope. It looks like this, but you can use the twist map, which I've mentioned here, to map yourself to a convex polytope. So I'll say something about that as we go along. So here I'll say a few words about totally positive matrices at the beginning and some other things. And I know Stephen will say some more tomorrow. So as I said, a totally positive matrix is a matrix all of whose minors are positive. Its origins, as far as I know, or maybe it goes back even earlier, are to Guntmacher, Krein, and Schoenberg in the 1930s. And one of the original motivations was actually vibrations in mechanical systems. So I'll just say a word about that. But it's applied to all sorts of other things. So diminishing sign changes in sequences. And then there's an application later to statistics and Markov processes. And so Samuel Carlin, for example, worked on this. And there's a whole book about basically the applications of total positivity to stochastic processes. And then more recently, there's been work on representation theory. So George Lustig at MIT generalized this to arbitrary Lie algebras, basically, and show how you can make sense of total positivity in that setting. And also here, actually, there's been this interesting application to high-energy physics. Nima Arkami-Hamid has applied it to the so-called amplituhedra, and I'll say something about that as we go along as well. So there are all these interesting applications of positivity. And as I said, what I'd like to link it to is a certain kinds of dynamics. One can think of different kinds of things. So the dynamics I'm going to look at is going to look like this. So this is related to the Toda lattice, but it's a little more general. So there'll be a flow that looks like this. So L is a given matrix. You can think of it as a symmetric matrix or you could think of it as I times a symmetric matrix Q Hermitian. And there's a flow that looks like this that can be generalized again to arbitrary Lie algebras. And here L and N, this is just a standard matrix bracket, but this has a gradient form. It's useful for us. It specializes to the Toda lattice, which I'll talk about. And there's some other related gradient flows that I'll talk about as well. Okay, so this flow that I just showed you actually has all sorts of interesting applications by itself, actually. So in fact, as I'll explain as we go along, actually, if you look at the equilibrium of this flow, it's actually a diagonal matrix. And what it can be used is to actually, it can be used to diagonalize matrices to do linear programming on permutahedra. And as I mentioned, it has this dual Hamiltonian and gradient nature when you relate it to the Toda lattice. And there's also an application to algorithms. This Toda lattice flow, a special case of this is actually the time one map of the QR algorithm, which is what you use to diagonalize a matrix when you use MATLAB, for example. So it has that nice little application. And it's related to other topological things like Morse-Smale diffeomorphisms. So let me say something just about this. I mean, it's not sort of crucial to the talk, but it just shows where it comes from, or at least part of the motivation. So Guntmacher and Klein looked at small oscillations of an elastic continuum. So you can think of a rod just oscillating. So it's linear. It has little oscillations, sinusoidal oscillations. So Y here is the deflection of the point X at time t. Phi is an amplitude function, and P is the frequency of oscillation. And in the general case, you have an infinite number of oscillations with frequencies P1 less than P2 and so on. And the idea is to consider transverse oscillations of n masses mi at movable points on this continuum. So this is what Guntmacher and Klein thought about for sort of engineering purposes. And you can define what's called an influence function, which gives you the deflection of a point x under the action of a unit point of a force applied at a point S. So I give a little push to the rod and things sort of move around. And this gives you the deflection of x under the action of this force. And if I set alpha ik equal to k of si, comma sk, two of those points, yi, the deflection, is given by this equation here. It depends on the acceleration. And it turns out this matrix alpha ik is totally positive. So that's, as I understand it, was the Guntmacher and Klein motivation for looking at totally positive matrices. So that's motivation, but not sort of crucial for the rest of the talk. And as I say, there are all sorts of other applications. For example, you can say a matrix is sign regular if all its k by k matrices are the same, all its k by k minors are the same sign, for example. And then there's something called the variation diminishing property, which people looked at. So if I take a non-singular n by n matrix, we say A is sign regular if the number of changes of strict sign in the order sequence of AX is less than or equal to the number of changes in X. So I take X, I multiply it by A and so on, and I look at the changes of sign. And you can show that if A is totally positive, then this is decreasing. So the number of sign changes decreases. So that's kind of an interesting property. So there's sort of work in that kind of study of sequences. And then, as I mentioned, there's this rather interesting recent application to so-called amplituhedra, which are generalizations of permutahedra, if you like. But this actually describes computations in particle physics. And I think this was certainly motivation for looking at the so-called totally positive Grassmannian and related things which occur in this area. So this was in physics right here. So that's kind of interesting. I think people are still interested. And so, in fact, with Stephen, we were able to prove some results on this. So there are conjectures about the topology of positive amplituhedra. They're still open conjectures, but we were able to prove some interesting things using this kind of analysis. Okay. So let me describe some of the background a little bit. So I'm going to sort of flip between the dynamics and the geometry. And I'm going to start by looking at the Scherr-Horn theorem, which is this rather beautiful theorem that's related to the moment map in geometry. So let me say something about that. So some of you may know this. So I have two sequences, d1 through to dn, and lambda 1 through to lambda n, sequences of real numbers arranged in non-increasing, at least in non-decreasing order. And then the Scherhorn theorem says there exists a Hermitian matrix with diagonal entries d1 through to dn, and eigenvalues lambda 1 through to lambda n, if and only if the sequence of inequalities holds. So if I give you a Hermitian matrix, I look at the diagonal entries di, and the eigenvalue is lambda I, then d1 is less than or equal to lambda 1, d1 plus d2 is less than or equal to lambda 1 and lambda 2, and so on, until you get the trace condition. So that's a rather beautiful thing. And so, so the Scher part of it basically is that, so Scher, I think this was back in 1923, proved this set of inequalities holds, and Horn in 1956 proved the inverse, that if I give you a set of numbers that obey this set of inequalities, there exists an Hermitian matrix with this set of eigenvalues and this set of diagonal entries, and it obeys these conditions. So it goes both ways. So the Horn theorem is sort of tougher to prove, but it's sort of still kind of interesting, just linear algebra. And the other interesting thing is that this is actually related to commutahedrons. What this really means is that if I take lambda 1 through to lambda n, and I take all its n factorial permutations viewed as a vector, and I take the convex hull of that, it gives me a commutahedron, and the di's lie inside that commutahedron, all right? And conversely then for the Horn theorem, if I give you the commutahedron and I give you a point inside it, I can give you a Hermitian matrix with that set of eigenvalues and this set of diagonal entries lying inside it. Okay, so that's the Scher-Horn theorem. So that's one of my favorite theorems. It's a rather beautiful thing. And it sort of generalizes in all sorts of interesting ways. So firstly, there was a generalization by Bertram Costant at MIT. So this Costant convexity theorem sort of generalizes to arbitrary Lie groups in the algebra. So it doesn't have to be a Hermitian matrix. It could be your favorite semi-simple Lie algebra. And then it also generalizes to the Hamiltonian setting, to the so-called moment map. So if I have a torus action on a suitable manifold, I look at its map to the, if I take this map, then it maps into the dual of the Lie algebra of the torus, all right? And that mapping actually is also convex. And this was proved by Atiyah and also by Gelman and Sternberg sort of back in the early 80s. So it has this very nice generalization to Hamiltonian systems. And it also plays a role in integrable Hamiltonian systems, and I'll say a bit about that as well. And then a sort of interesting special case of that, which is related to what I'm going to talk about here, is instead of applying it to the whole Lie algebra, you can apply it to a subspace of that, the so-called Jacobi matrices. So Jacobi matrices are tridiagonal symmetric matrices, which play a big role in integrable systems and in orthogonal polynomials. They're interesting for lots of different reasons. But you can also show using dynamics, in fact, that the set of Jacobi matrices with a fixed set of eigenvalues is diffeomorphic to a convex polytope, just like this one. And this uses this twist mapping that I just mentioned to you. So let me just say a word about the proof of Scher, just because it's sort of somehow related to what we're going to talk later. And sort of Horn is the other direction. So let's say if I take A to be a Hermitian matrix with eigenvalues lambda I, let's suppose I take A equals, sorry, this shouldn't be an A here. So I diagonalize it, I put lambda equals UA, U to the minus 1, where U is unitary. Then you can check that AAI is just equal to sigma j equal 1 to n, lambda j mod uj ij squared, where U are the entries of this unitary matrix U. And if you let S equal to Sij, so Sij is equal to mod Uij squared, U unitary implies that S is doubly stochastic. So that's the key thing here, that there's a relation, there's a doubly stochastic matrix, so that means it's both rows and columns add to 1. Those are sort of nice objects which play a role in Markov processes, but also interesting here. You can check that A equal to S lambda implies that A is equal to the convex hull of these lambdas. That's exactly what I mentioned earlier. And this is related to some work of Birkhoff, the so-called Birkhoff polytope, which says that the set of all n by n doubly stochastic matrices is a convex polytope. and the polytope is the convex hull of the permutation matrices. So that's what it follows from. So that's Bloch's theorem, which goes back also, I guess, maybe to the 1920s.
What is the relationship to the convexity of the image of the moment map?
So this is the convex. So this is exactly the convexity of the moment map. So if it's so in this particular case, I have the unitary group. I have the unitary group acting on a given matrix A, and that gives you a torus action sitting inside the unitary group, and that torus action gives rise to the moment map. So that's the map here.
And so the map is like you take a matrix to its eigenvalues, basically.
Yeah. So the map actually is you take a matrix. If I take a general matrix, I actually just project it onto the diagonal. Actually, so I take the matrix, I project it onto the diagonal, which is the Lie algebra of the torus, and then the map is to the dual of that Lie algebra.
So then the convexity of the moment map applies the horn.
Yes, right. So that's right. So that's the horn part as well. Right. So that's yeah. So that's sure horn, and yeah. So and as I say, you can apply quite generally to sort of the action of a torus on more general manifolds. Okay. So we'll come back to that. Oh, and one thing I should say also, we also applied, so we're interested in for Toda. So for the Toda lattice, you don't have the full matrix. So the Todas, you'll see it's tridiagonal matrices, as I mentioned. So that if you apply the moment map to that and you project onto the diagonal, it's not entirely obvious what you're going to get. And in fact, if you do the naive thing, you get something that's not convex. So you have to do something else. All right. So it's sort of context dependent. All right, so let me say something now about totally positive matrices and how they extend to flag manifolds and Grassmannians, which is the thing that we were sort of working on recently with Stephen. So let's look at FL and FC. So this is a complete flag variety consisting of all sequences of nested subspaces of Cn. So V1 to Vn, I just take a nested sequence of subspaces, such that each Vk has dimension k. And you can view this as the quotient of GLNC by the subgroup of upper triangular matrices. So it's just GLNC mod Bn of C. And in fact, upper triangular matrices play sort of a crucial role here. And so you can think of Vk as the subspace spanned by the first k columns of the matrix representation of GLNC mod Bn of C. And Lustig, as I mentioned, who played a key role here, introduced two remarkable subsets of the real points of FLNC, called the totally positive and the totally non-negative flag varieties, which we'll denote by FLN greater than 0 and greater than or equal to 0. All right, so how does that relate to totally positive matrices? So if I take the subset of GLNC of totally positive matrices, so then we go to matrices again with all mine is positive. And then FLN greater than 0 is the image of GLN greater than 0 inside this space, GLNC mod BNFC. And then an FLN greater than 0 is its closure. So you simply just map totally positive matrices onto this set. And there are several ways to think about it. You can think of it also as the set of flags, which can be represented by an element of GLNC, whose left justified minors are all positive. All right. So those are equivalent representations of the totally positive matrices, right? And at least the totally positive flags. And then, of course, you can think of special subsets of this which are interesting. So I don't need to have a complete flag. I don't need to have all its subspaces. I could just have some of its subspaces. There could be a gap. So for any subset, you can have the partial flag consisting of nested subspaces of dimensions k as an element of k. And again, you forget about certain subspaces. And it turns out that, they're actually, it's rather important whether you have a complete flag or you don't, and they have sort of very interesting properties, and partial flags turn out to be kind of subtle and interesting with respect to positivity and other things. Okay. So a particular case of interest is the Grassmannian. So the Grassmannian is basically where I just have one subspace, I'm sure most of you know this very well, but the Grassmannian is a sort of beautiful manifold. So basically the Grassmannian in either the real or the complex case is just the set of so in this case, k-dimensional subspaces of Rn, right? So I just look at Rn or Cn, I look at the space of all d-dimensional subspaces. So it's a very special case of the flag. And as I mentioned, this has played a big role in various things. So you can think again, just using this definition about the totally non-negative or the totally positive Grassmannian. And this object is particularly interesting and it's played a role in lots of different areas. As I mentioned, in particular, there's representation theory going back to Lustig. There's combinatorics due to Posnet-Tehoff. It's related to cluster algebras and to high energy physics in the way I just mentioned, and even to symmetry, to mirror symmetry and so on. So it sort of plays a role in lots of interesting places. And what we can do here is sort of view it in a dynamical way. So you can take a partial flag variety, and remember I just looked at conjugations of the matrix lambda, sort of u to the -1. So you can view a partial flag variety like I just did, or you can view it as an adjoint orbit inside of the algebra, right? So how do I get a general flag? I just sort of fix a diagonal matrix. I choose a set of eigenvalues. If they're all the eigenvalues are different and I conjugate by a unitary matrix, then I get a complete flag. If the eigenvalues are all 1, 1, 1, 1, and then just zeros, I get the Grassmannian. And if some of them are equal, I get something in between, which is a general flag manifold. So you can just view it as a sort of nested subspecies of spaces, or by conjugating a certain kind of diagonal matrix, which is sort of the dynamical picture that's useful to have in mind. And you can relate this to dynamics and the total lattice in the way I just showed you. And so the work here that I want to talk about is actually related both to the dynamics and to this total positivity. So the first piece of it is related to some earlier work that Stephen did with Galashan and Lamb. And what they did is they constructed a contractive flow on the totally non-negative partial flag variety in order to show that it's homeomorphic to a closed ball. All right. They first showed it was true for the totally positive Grassmannian, and secondly, they showed it's true for an arbitrary flag manifold. And one of our goals here was to show how to look at these flows in a more general and sort of geometric context. And basically what you use are contractive flows, which are gradient flows on an adjoint orbit that I just discussed. And in fact, these flows have played an interesting role in the work of Peter Brandon recently. And for example, he showed that you can actually show that the space of stable polynomials and Lorentzian polynomials are equivalent to closed balls as well. So this is related to his work with June Her. And so the flow actually sort of is based on the kind of flow that Stephen and Galashan and Lamb used. So some of these geometrical ideas we're hopeful will apply also in that context. So this is something we've been thinking about recently. The other piece of work is something I mentioned earlier about the Toda flow on an adjoint orbit. So that tridiagonal flow that I showed you can be generalized to arbitrary adjoint orbits, sort of again, a la constant. And what we can show is that after applying a certain involution, the flow becomes a gradient flow in a Kähler metric, and projecting by the moment map gives you a homeomorphism from the isospectral manifold, again, conjugating by a unitary matrix onto the moment polytope. So that sort of puts these things together. And what you can do is you can use this sort of flow to get these sort of geometrical results about a ball for these totally positive flags or totally positive Grassmannians. And as I mentioned, it's a little subtle. You have to introduce this notion called the twist map that I'll describe. And so what we want to do is sort of link the twist map, this total positivity in geometry to these flows. So that's what I'll show you. So any questions about that? Okay, so let me, so I'll say something about the flows and I'll come back to total positivity. So the gradient flows that we're looking at are on adjoint orbits, as I mentioned. So you just think of conjugation. And it turns out, and this goes back to Attia's paper actually, that there are three natural metrics on an adjoint orbit. There's the so-called there's the Kähler metric, since it's a complex manifold. There's the normal metric, which plays an interesting role here, and the so-called induced metric. So I'll say something about what they look like. And what we do is we look at those flows which are compatible with total positivity. So if you're trying to say something about the topology of a manifold using flows, so that's sort of like the Ricci flow or something like that, you'd like to know that it preserves the properties that you're interested about. So for example, so you want to know, for example, if you take a flow on a manifold, does it preserve total positivity? So one of the things that we studied was exactly that, which flows and which metric preserve total positivity. And then we'll relate them, as I said, to some of these other things. Okay, so let me say something about the Toda flow. So I'm going to relate it sort of quite clear, explicitly in terms of coordinates, and you'll see it sort of relates a little bit to the moment map and to the Chur or in polytope that I just showed you. So this is an interesting bit of mechanics again. So Toda, I think, probably goes back to the 50s and 60s. So this is a mechanical system that describes the interaction of particles in a line in one dimension. So that's the Toda lattice. All right, so it's a bit like the symmetric exclusion process, which has been used in stable polynomials. You've just got a bunch of particles on the line, all right, and they're interacting under a certain potential, which I'll show you. And we're interested in the dynamics. So Toda was a solid state physicist, and he wanted to come up with a system that is explicitly integrable. And it's sort of also related to, the famous work of Fermi, Pastor, and Ulam during the 1940s when they were looking at equipartitional energy for interacting particle systems back in Los Alamos. And they noticed that if you took certain systems, equipartitional energy didn't happen. All right, the energy sort of stayed localized, and that was because the system was solvable. And they used systems that were sort of close to the Toda lattice, but not quite. But this system sort of encapsulates that kind of integrability. And so, if you think about integrable systems, they're sort of two famous classes, basically, of integrable systems. You think of Toda lattice type particle systems like this, and rigid body type systems. So another integrable system, again, it's not that obvious to take the rigid body, which is a complicated thing that sort of wobbles around in space. But again, it's solvable in terms of elliptic integrals. And the Toda lattice, you can think of it you can think of it on the line, you can think of it on the circle, and in the latter case, you get what's called the periodic Toda, but we're going to look at the particles basically on the line. So this is n particles moving freely under the x-axis, and it's under an exponential potential. So this is the Hamiltonian for the system, which is the energy. So I just have sigma yk squared, that's the momentum, and I have this nearest neighbor interaction, which is exponential. So sigma k equals 1 to n e to the xk minus xk plus 1. And then the Hamiltonian equations are just these equations here. So you can think of it evolving on the line, but actually it's convenient to sort of contract it onto a sort of finite dimensional space. So this is what's called the finite Toda lattice. And this was actually first described by Jürgen Moser in a rather beautiful paper on the finite Toda lattice. And so that just means you have these boundary conditions, e to the x naught minus x1, and e to the xn minus xn plus 1 is equal to 0. So that formally corresponds to setting one of the particles at minus infinity and the other particle at plus infinity, right? Because if you put, say, xn plus 1 at plus infinity over here, this guy goes to 0. So that's the finite Toda lattice as opposed to the Toda lattice on the line. So you could look at an infinite lattice, if you like, and there are all sorts of variations of this. And I'll come back to another one later on. That's the lattice, it's Hamiltonian. But the thing that connects it to geometry is you can show that there's a Lax pair. So this goes back to the work of Peter Lax, and is crucial for integrable systems. So there's this simple transformation. In the beginning of these things, it's always simple, but it's actually hard to find because there's no recipe for finding a Lax pair. So let me just show you what that is if you haven't seen it. So I just make this transformation. I said AK equal to this. That's essentially the position variables. I said BK equal to the YK, which is the momenta. And if I take the new set of variables, I get this set of equations with these boundary conditions. So it doesn't look super interesting, but it actually is, because you can rewrite it in a Lax pair form, which is L dot equals B bracket L, where L is this tridiagonal symmetric matrix. So here we get the tridiagonal matrices. So the B's are on the diagonal, the A's are on the off diagonal, and B is the skew symmetric part of L. And you can show the system is integrable. And it's actually not too hard to see that. So what is an integrable Hamiltonian system? Well, it actually means it's solvable. But there's this famous theorem of Arnold, often called the Arnold-Liouville theorem, that tells you a system is integrable. Say it's on a symplectic manifold of 2 n dimensions. Basically, you have n integrals of motion that commute under the Poisson bracket. So you basically need n commuting integrals. That's an integrable Hamiltonian system. And that's true for the, as I said, for the rigid body, for some n-dimensional generalization of the rigid body, not to other systems. I mean, the actual history is this was first found by Peter Lax for the famous KdV equation, which is an equation for sort of shallow waterways. But then it was shown that it can be applied to lots of other systems. So this was, yeah, I mean, this sort of set a kind of renaissance in the integrable systems. And for example, Philip Griffiths, who is here, was really interested in that, has written a beautiful paper about different integrable systems. And it is related also, interestingly enough, to algebraic geometry. So if the system is periodic, for example, you can show if you just take the characteristic curve of the system, you look at delta L minus lambda I, that gives you an elliptic curve, and you can show the system linearizes on the so-called prim variety of the elliptic curve. So there are all sorts of interesting connections to algebraic geometry.
So here, this matrix B, it depends on the time.
Yeah, so it's all time dependent, right? Exactly. And I'll write in a second with a matrix N that's fixed, but yeah, it depends on the time. So it's a nonlinear system. And so so it's actually kind of miraculous. I mean, so first of all, why is it tridiagonal? So it's tridiagonal because it's nearest neighbor. Each point only talks to its nearest neighbor. You can get their sort of diagonal versions of this, but it's actually not that obvious. So if I write 2 general tridiagonal matrices and I take their bracket, AB minus BA, there's no obvious reason why it should still be tridiagonal. But again, it has to preserve that. But if you do that, you can check it is tridiagonal and you get a closed system of equations, and these are they. All right, so it's not at all obvious. And again, you can generalize this to arbitrary Lie algebras, to the rigid body on the Toda orbit and things like that. And so again, Costin played a big role in that. So he did a beautiful generalization looking at the Toda lattice. We often call it the Costin Toda lattice. You can generalize this to an arbitrary set of Lie algebras. And Costin also played a role in convexity, as I mentioned, which sort of connects the two. So yeah, let me just say something. So let me just show how it relates to convexity as well. So here's the way to think about it. I mean, there are other ways of thinking about it, but this is a rather beautiful way of doing it. So for example, so let's suppose I choose another matrix now. So this is going to be a constant matrix, and this is kind of the cute thing. And it applies to the flows I'll show in a moment. So let's take n to be the matrix diagonal 1, 2, 3 through to n. I'll simply take a matrix n, which is diagonal, all right? And it has the entries 1, 2, 3, 4, 5, 6, 7. So the important thing is it's just a sequence of consecutive integers. It could be any sequence, actually. And then you can check that you can rewrite the flow in this form, L dot equals L bracket n. And L bracket n is actually just equal to minus B. So it's an easy thing to check. So for example, if you look at this, and this is kind of a fun but crucial fact, if I take this matrix B, which is skew symmetric with zeros on the diagonal, I can get it from L just by taking this matrix bracket with n. So since n is a diagonal matrix, if I take L bracket n, the diagonal entries go to 0. And since the matrix is just consecutive integers, 1, 2, 3, 2, and throw to n, you can easily check that all it does is it puts a plus sign in front of all the a's and a minus sign in front of all the a's below the diagonal, and the rest is 0. So that's it. So that's kind of a cute thing. Why do I care about that? Well, this turns out to be a gradient flow. So choosing the right metric on an orbit, you can check that this is the gradient flow of the function trace Ln, which is not the Hamiltonian. So it has to be something else. But it turns out, and this is kind of a rare thing, that the Toda lattice flow is both Hamiltonian and gradient. So it's Hamiltonian that conserves an energy, and it's in gradient in the fact that it decreases this guy, trace Ln. So how can that be?
Is it a flow on a set of tridiagonal matrices?
Yeah, it is. There's a flow on a set of tridiagonal matrices. But you can generalize it to symmetric matrices, and I'll come back to that. But it's a flow on the set, And the way you can think about it really is since the eigenvalues are preserved along the flow. So if I look at this guy here, that's one of the crucial things. You can check that, the Hamiltonian turns out to be the trace of L squared, and the other computing Hamiltonian is the trace of L cubed, L to the fourth, and so on. That's easy to check. If I just take the derivative of trace L to the n, you can check that it's actually, those are all zero. And so that means it's an isospectral flow. And you can think of the conserved integrals as either the eigenvalues or the traces of the powers of the matrix L. And the interesting thing, as I mentioned, is that it flows to a diagonal matrix with entries on the diagonal that are just the eigenvalues. So the beautiful thing, as I said, it's a way of diagonalizing things. If I look at the long time flow on the space of diagonal matrices, you can check, and it's sort of easy to see from this double bracket form. So if you think about it, if it's an isospectral flow, it conserves the eigenvalues, and n is diagonal. So when is this going to be zero? Well, by elementary spectral theory, only when L and N commute, right? So when do L and N commute? Well, since N is diagonal, L has to be diagonal. So the only possible, and since it's isospectral, that the eigenvalues have to be on the diagonal. So the only possible equilibria of this thing are the set of eigenvalues, right? And in fact, there are n factorial of them. So there are n factorial eigenvalues, the permutations of the eigenvalues. And this is exactly the Scherhorn polytope. So if I think about it, sort of what it looks like, there's my polytopes. This is R3. And then so I have, so one of the equilibria is lambda 1, lambda 2, and lambda 3. And the other equilibria are just the permutations. And then, if you like, I can invoke the Scherhorn theorem. I can look at the diagonal of L, and I'll see a flow inside the polytope, right? That's Scherhorn, all right? So it connects rather beautifully with Scherhorn, and it sort of minimizes this function of trace Ln, and in fact, it goes to a permutation which maximizes or minimizes trace Ln. So if n is 1, 2, 3, so on through to n, it has the rearrangement has to be lambda 1, lambda 2, lambda 3. That's the stable equilibrium. So it's actually like the moment problem, or Littlewood's moment problem. So you want to put the biggest eigenvalue with the biggest value of 1, 2, 3, and so through the n, and so on. So that's what it'll do. And so the interesting thing is, as I said, it's not quite the elementary Scherhorn problem because it's only tridiagonal matrices. So if I map the thing, I actually I end up with a sort of subset inside this polytope. But but you can show, using what I'm going to show you is the twist mapping, show that the set of all triangle matrices actually is essentially homeomorphic or diffeomorphic up to the edges of the polytope. So that's Toda. And so let me just show you a sort of picture. So this is, for example, this is four-dimensional Toda. These are the equations of motion. And trace Ln in this case, the thing you're minimizing, just turns out to be equal to the one thing, B2. And you can check it decreases along the flow. And this is actually the dynamic. So if you just look at the diagonal entries, in fact, any of the entries, what you can check is that you can choose any initial conditions. The A's go rapidly to 0, and the diagonal entries head to the eigenvalues. And this is, as I said, it's really just like diagonalizing a matrix in MATLAB. This really is the time one map of the QR algorithm. So it's actually an effective way of diagonalizing the matrix. So it has that rather beautiful property. Okay. So the other things actually, and this is not super important, but it's kind of interesting and relates a little bit to what I'll say into to Grassmannians, and in fact, the particular case of the projection space. Since you preserve the eigenvalues, you can think of those as kind of fixed along the flow, and then you can look at a conjugate set of variables, sort of action angle variables for the problem, and you can rewrite the flow in terms of, in fact, the top components of the normalized eigenvectors. This is what Noser did actually in his paper, and then you can rewrite it also in a sort of double bracket form, but on projection matrices. This is a rank 1 matrix, RR transpose, where R is the set of the top components of the normalized eigenvectors. And so this is another interesting way of looking at the flow sort of on the set of fixed integrals of motion. Okay, so I'll come back to that kind of picture. Yeah, so again, I just drew that for you. This is the Scherhorn polytope. All right, so now I want to sort of relate this all back to total positivity, right? So we looked at the general description of total positivity. We looked at the flows. Let's see what the flows can tell us about total positivity. So as I said, one way to think about flag manifolds or Grassmannians as orbits, and that's what we want to do. So so adjoint orbits here. So I let U of n here denote the group of n by n unitary matrices. I take a weakly decreasing sequence lambda 1 through to lambda n, and I consider the adjoint orbit inside the Lie algebra of matrices with fixed eigenvalues. So I just take lambda 1 through lambda n, and I conjugate. I get myself an orbit. And as I mentioned earlier, you can identify that orbit with the partial flag variety, where k depends here on the multiplicities of the entries of lambda, right? So there are several possibilities. I could end up with a complete flag, I could end up with a Grassmannian, or I could end up with something in between. And so in the generic case, I have the complete flag. At the other extreme, there's the Grassmannian. And you can represent the Grassmannian in lots of different ways. So this plays a role in our work. So you can represent the Grassmannian, it's just a D-plane in n space. You can represent it by a D by n matrix, or you can represent it by the projection onto the plane. And that's what we do. So if you're used to thinking about it as a D by n matrix, you just take essentially you just compute a projection onto that plane, which is V star V into the inverse times V, basically. But you can compute the projection. And the totally non-negative part of the flag describes a corresponding subset of the orbit. So that's the non-negative part of an adjoint orbit. So it's a distinguished subset of a set of purely imaginary matrices in the orbit. So you can describe for yourself the totally positive part of an orbit this way. All right. So you can think of the orbit, and I can think of the non-negative part of the orbit in the sense that I described to you earlier. And so there are a number of results. So I want to relate these to some of the results that I mentioned earlier about from Lustig and so on, and to the dynamics that I just described. So I'll go through these in the remaining time. So let's suppose that lambda 1 greater than lambda n, and so is greater than 0, and IL is an element of one of these positive orbits. And you can see that IL is in this orbit if and only if L is eventually totally positive. So L to the M is in GLN greater than 0 for some n greater than 0. So that's one result. If lambda is omega k, that's the Grassmannian case, then you can check that IL is totally positive if and only if all the k by k binders of L are real and positive. So that's sort of a special case. You need fewer minors in some sense if it's the Grassmannian case. And then there's the tridiagonal case, which you've just been talking about. So if L is tridiagonal, then IL is in a totally positive orbit, if and only if L is real and its entries immediately above and below the diagonal are positive. So the tridiagonal case is sort of really simple but kind of beautiful. So if I go back just to the Toda for a second, so if I take a tridiagonal matrix and you want that to be totally positive, all that you need is that the entries above and below the diagonal are positive. That's enough for total positivity. So you don't have to check all the minors. You can just have a quick look at it. And the beautiful thing is about Toda, remember the age with e to the lambda I minus lambda j, basically. So it's already positive because they're exponential. So the natural matrix coming out of Toda is a totally positive matrix. So that's kind of convenient. So that's that. And then so the tridiagonal subset is actually known as the set of, as I said, of Jacobi matrices. And as I said, we need something called the twist map to show, in fact, that the polytope that you get out of the tridiagonal matrices is actually a polytope, and for other things as well. So we introduce an involution on the flag called the twist map. So it's also a very simple thing to write down the way, but it's kind of deep and interesting. So I'm given a V, a sort of a subspace in the flag, which I can represent by a unique orthogonal matrix whose left justified minors are all non-negative. Then the twist map is simply this object here. I just take G, I take its transpose, GJI, and I multiply it by -1 to the I plus j. That's the twist map. So it's a very simple action on matrices. So basically, you're just inverting or transposing G and changing the sign of every other entry, right? So simple linear algebra. It's a rather beautiful object. It plays a big role in integrable systems theory, plays a big role in what we do in total positivity. And the amazing thing is this operation is compatible with total positivity. If I take a totally positive matrix and apply this twist map to it, the matrix is still totally positive. Not entirely obvious, but it's true. And so it defines an involution on the totally positive flag in particular, and the non-negative flag.
Is it the restriction of some natural map on the complex flag variety?
On the complex, right?
Complex black variety. It's this
Oh, on the
map.
complex flag variety. Yeah, no, I guess, no. So you say no. Yeah, it's not obvious.
Yeah, kind of for topological reasons. But basically you have a flag and you want to represent it by an orthonormal basis.
Yeah.
But there's, over the real numbers, there's signs you need to pick. So total positive, if your flag is totally non-negative, it tells you how to pick the signs, but there's not going to be a consistent way.
So it doesn't extend at all.
Oh, I see what you mean.
Yeah,
Right. No, that's right. Yeah, so it's right. It has to be restricted to the totally positive part. I mean, this also plays a role in the Toda lattice. Yeah, so in fact, right, it's really important. So even for the Toda lattice, when you need to try and explain the convexity, you need a very sort of special. You have to apply the twist map in a very special way, right? It's not. It doesn't apply to a general flag.
Is there sort of any conceptual reason why one might do this map?
Well, the conceptual reason, yeah. So it's to make it. So for me, the original motivation was to make it compatible with the with the action of a torus. So, for example, if you take the Toda flow, the integrals give you the action of a torus on the underlying manifold, but it's not actually the standard torus action, which gives you the moment map. So to turn it into a good torus action, you have to apply this twist mapping. So that's one reason. And the other reason is to sort of make it, as I think will become clear, for the applications to total positivity. So it's to make it sort of compatible with the geometry and dynamics. Because otherwise the natural maps, the natural dynamics, the natural maps give you the wrong thing. Yeah. So it occurs in other places actually. So so here is just an example of the twist map, which does exactly what I told you. See, there it is. And so it does occur in the work of Berenstein, Fomin, and Zelevitsky on cluster algebras. It's sort of based here on the Iwasawa decomposition, so you can sort of apply it quite generally. They have this other thing that's related to the Bruja decomposition, but it's also important in Poisson geometry. In fact, so here, so you can contain a corresponding evolution on an orbit, and this turns out to be the so-called dressing transformation in Poisson geometry, actually. So it's related to the geometry of Poisson Lie groups. So I'm not going to say anything about that here, but it does appear there. Yeah, so here lambda is a diagonal matrix with the standard entries. G is chosen to be left justified, minus on non-negative. And the important point here is that G to the minus 1 lambda G depends on G and not just on the element of the orbit. So in a sense, I guess that answers your question. And total non-negativity provides a canonical way of selecting this representative. So the important thing here actually, so one of the weird things actually in the original work that I did on Toda is, I mean, really what it is you just take the G to the minus 1 lambda G and you flip them, all right? But if you do that, you need a canonical way of representing you need a canonical way of selecting this representative G. And that's not so obvious how to do it, but total positivity gives you a way to do that. So I'll come back to that if I have time. So let me say something now about the gradient flows, and I want to say something about how this shows you total positivity. So as I said, you want to look at gradient flows that preserve positivity because we want to say something about the underlying topology of the manifold. So you want a flow that sends O lambda greater than 0 back inside it after positive time. So we look at these kind of total lattice flows like trace Ln. And as I mentioned, there are these three different metrics which play a sort of role originally in Atiyah's work, the Kähler normal and induced metrics. And what we were able to do is to try to classify, or at least we want to classify, which flows strictly preserve positivity. So we were able to get sort of partial results, but we were able to get the results that matter to us. But the interesting thing is if you take the Grassmannian, which is the first thing that people looked at, the three metrics coincide. So there's three different metrics on an orbit. On the Grassmannian, they're all the same. And the nicest one to think about is the so-called Kähler metric. So this is what you can show, for example. So if I take the gradient flow trace Ln on the Grassmannian, you can show that it strictly preserves total positivity if and only if In is real, Nij is equal to 0 for I minus j, not equal to -1, 0, or 1. So it's sort of tridiagonal, and at least n minus one of these inequalities are strict. So you can get a very precise characterization of when it preserves total positivity. But the interesting thing is if you look at the general flag, then it's not nearly so obvious what preserves positivity, and in general it doesn't work. So for example, you can show in the case of the Kähler metric, it preserves total positivity. In the case of the other two metrics, it's not absolutely clear. So for the so-called normal metric, which is what I use for Toda, it doesn't preserve total positivity. And in the so-called induced metric, it depends on the eigenvalues in an interesting way. Okay, so is that. So what you can show here, so this says that if, let's suppose I take lambda non-decreasing, at least three distinct entries, I look at the gradient flow again. In the Kähler metric, it strictly preserves positivity if and only if In is a real tridiagonal matrix whose entries above and below the diagonal are positive. And as I said, in the normal metric, there are no flows that preserve positivity. And in the induced metric, it's really complicated. So this is what I just said. So then, oddly enough, it depends in a way that we don't understand on the eigenvalues of the system. So even though I have an action of your view on the group, at least on the algebra, it actually depends on the spacing of the eigenvalues, and they're all complicated in interesting ways. So that's sort of still kind of under construction. So now I want to relate it to the work of Galaschen, Kopp, and Lamb on total positivity. So what did they show? They showed that there are certain flows which strictly preserve total positivity, and they can show that the partial flag variety is homeomorphic to a closed ball. And that's essentially what we want to do here. So what to do that is I look at this double bracket flow that I just showed you, L bracket Ln. So what you can show is the following. So suppose that I have lambda and mu in Rk, and lambda k is greater than k plus 1. I consider the gradient flow of trace Ln in the Kähler metric. And as I said, it's all the same on the Grassmannian. So if S is a non-compact subset of the stable manifold of the global attractor, what you can show is that any flow starting in S remains in the interior of S for all time. And that means that S is homeomorphic to a closed ball, its interior is homeomorphic to an open ball, and its boundary is homeomorphic to a sphere. So this is basically what we do for the totally positive matrices, at least for the totally positive orbits, the matrices. So if we apply this theorem in the setting of the gradient flow, we obtain that O lambda greater than 0 is homeomorphic to a closed ball, and this recovers the result of Galaschen, Kopp, and Lamb. So basically what you're doing is you're taking the flow, trace L bracket N, you let it act on the totally positive part of the orbit, and you can show it flows to a point, basically contracting it down, and that shows it's equivalent to a ball. So that's the beautiful thing. And so that sort of recovers the results of Galaschen, Kopp, and Lamb in this kind of geometric setting, but there are also applications to other things. So for example, as I mentioned, one of the interesting applications of totally positive matrices are these so-called amplituhedra. But let me say a word about that. And so there was questions about what the topology of these things are. So what is an amplituhedron? And I don't pretend to know too much about the particle physics, but this is where it comes from. So this is a generalization of the totally non-negative Grassmannian, and it was used to calculate scattering amplitudes for supersymmetric Yang-Mills theory. So it has this great physics application. So the idea is that it's basically the Grassmannian, but plus a certain auxiliary matrix, K plus N times N, called Z. And M here is an additional parameter satisfying these conditions. And as I said, there's people are really interested in this and the combinatorics and topology of amplituhedra. And there's this conjecture, which as far as I know is still open, right? That every amplituhedron is homeomorphic to a closed ball. And there are certain cases where this was known. So when K plus N is equal to N, you can show it's equal to a closed ball. When K is equal to 1, it's a so-called cyclic polytope. And so there are other special cases. And what we were able to do using the techniques here is come up with a new family of amplituhedras, if we call them the so-called twisted van der Monde amplituhedron. So you take one of these amplituhedrons, you twist it by exactly the twist map that I just showed you here. So what is the van der Monde amplituhedron? You take the amplituhedron for which the matrix Z arises by applying the twist map to the so-called van der Monde flag, which comes from the van der Monde matrix. And this includes this set of amplituhedra here satisfying these conditions. And you can show that every twisted van der Monde amplituhedron is homeomorphic to a closed ball, its interior is homeomorphic to an open ball, and its boundary is homeomorphic to a sphere. So using this bunch of geometric techniques, et cetera, we were able to come up with a new class of amplituhedra that we know is homeomorphic to a closed ball. Okay, so I'll sort of end up just by coming back to the Toda lattice. So one of the nice things is, so the Toda lattice I showed you is tridiagonal. You can actually write down the Toda lattice for a full symmetric matrix as well. All right, so instead of tridiagonal, it's full symmetric, and the B matrix is just the skew symmetric part of the L matrix. So it's L is symmetric, B is skew symmetric, and again it preserves it, right? So if I take L dot equals L bracket B, symmetric bracket skew symmetric is symmetric. It's a nice well-defined flow. And so what you might wonder is that flow also a gradient flow? All right, that's also not that obvious. But what you can do is show that's true here as well. So the Toda lattice, it also turns out to be integrable. It revolves on an adjoint orbit. It's actually much less clear it's integrable because you have lots of variables. But it actually is integral. This goes back to some work of Percy, Dykes and collaborators. So it's not just the traces of the powers. There are a whole bunch of things, actually. It really depends on, in some sense, on the minors again, just like total positivity. Anyway, you can show that the Toda lattice flow is a gradient flow which weakly preserves total positivity. So in the tridiagonal case, it's a gradient flow in the so-called normal metric, which I haven't shown you in detail here. But in the general case, you can show it's a twisted gradient flow. So what we were able to show, again, if lambda is strictly decreasing, I look at the Toda flow beginning at a point in the orbit, the totally positive orbit. Then theta lambda, the twisted L, is a gradient function of the function trace Mn in the Kähler-metric, where In is the diagonal entries, the diagonal matrix with entries lambda 1 through to lambda n. So using the twist map, you can show that not only is the tridiagonal Toda gradient, but the general Toda is gradient as well. And that actually sort of generalizes this result that I did earlier with Flasker and Rustu. And the beautiful thing is, it's sort of it was kind of complicated, but using total positivity, but you use total positivity in the twist map, you can show this in a kind of beautiful and elegant way. And that sort of was the last piece of this paper that I wrote with Stephen. So that's pretty much it. So I'll sort of stop here, but since I've run out of time, but yeah, so just to give you just one last slide. So how do you get the metric on an orbit, just for a moment? So if I take an orbit, you're just acting by the group. So tangent vectors of the orbits are things of the form L bracket X and L bracket Y. And then really the different metrics are just how you pair these together. So for example, to get the normal metric, you take L bracket X and L bracket Y, and the metric is just trace X, Y, basically, where you ignore the part of L. So it's the part of X that doesn't commute with L, and you take the part of Y that doesn't commute with L and you pair them together. That's the normal metric. And that's how you get the double bracket flow and the Toda flow and so on. And the other metrics, and the place to look at this if you want to see more about that, and it's kind of fun, is if you look at a TIA's paper or you reproduce it in our paper, you can look at these different metrics. And the different metrics have different flows and different ways of preserving positivity and so on. So this is kind of a rather beautiful story in itself. All right, so I've used up my time. Thank you very much. You'll hear more about total positivity from Stephen tomorrow and other applications. All right, thank you very much. Yeah.
In what sense is the Toda lattice a lattice?
Oh, it's just that it's a one-dimensional lattice. So, yeah, so it's actually a good question. So for the tridiagonal Toda, it's a one-dimensional lattice. So we start off with the particles on the line, and it's e to the xi plus 1. So it's a simple one-dimensional lattice. On the other hand, the full Toda, which I just talked about, actually isn't a lattice. It's just you take the matrix and you make it full. So you can try and generalize it to a big, say to a two-dimensional or an n-dimensional lattice. You can write it down, but those are not known to be integrable for some reason. So this particular generalization is, but yeah, the total lattices in higher dimensions exist, but are not integrable, at least as far as we know. Yeah. But yeah, it's just a lattice. Yeah.
Do you expect total positivity for other versions of the Toda lattice, for example, periodic Toda or maybe relativistic Toda?
Yeah, so that's a good question. So we're just working on that right now. Yeah, so this is all, you're right. So they're all both interesting, non-relativistic Toda and periodic. Yeah, I think so. So how do you write periodic Toda? It's actually on the loop, so it's on a loop group, right? So you have to generalize what we just did here. In fact, you need to go to Kac-Moody Lie algebras. That's what it is. So you go from the ordinary Lie algebras to Kac-Moody Lie algebras. And I believe, our belief is, yes, you can do it. But it's actually work in progress. So there was work by Thomas Lamb and others on total positivity on loop groups. So here we need total positivity on orbits like we did here. And we were literally talking about this yesterday. So it's ongoing work. I think that's a great question.
What's the relationship between the old proof of the boldness and the new proof of the boldness?
Right. So in that case, they had a sort of very particular flow, which was related to, I guess, nearest neighbor transpositions on the matrix. So what basically they have something in the form of e to the minus lambda t, which was a contraction. So, I mean, Stephen could say more, I guess, but basically my understanding of that is there was just a contraction on the space of matrices, like e to the minus lambda t, but it didn't obviously come from anything geometric. It wasn't a gradient flow or anything like that. So as far as that's concerned, we were just able to recast it in terms of these gradient flows, but having the gradient flows enabled us to prove total positivity for other things. But it's a different, I guess the answer is it's a different contractive flow. So it's equivalent to a wall, those particular cases.
Old proof was more like, and the new proof is more geometry-like.
Yes, I would say so.
Yeah, I say the original proof, we sort of just defined the flow.
But how did you find that one? What was the?
Yeah,
It was just a guess that turned out to work. But here we wanted to show, like, what does it mean geometrically? Is it a gradient flow if so, with respect to which vector field and what metric and so on. So we didn't have that before.
Right. And I think this sort of, and these sort of flows, I mean, as I said, these double bracket flows live naturally on grass mullions and orbits and so on. So it's kind of a natural thing to think about it in retrospect. And so we try to do the same, by the way, for stable poly. If you look at the SEP flow in that paper, Peter Brandon and so on. So I've tried to do it, and we're still thinking about that.
That's more like the first.
Exactly. It's very similar, but not quite the same. We were just talking about that. So exactly. So I would like to try and get into this geometric context. We haven't quite been able to do that. We're still working on it.
Okay, if there are no more questions, let's think. How many one more time?